Welcome back. Today we shall learn a multivariate quantitative approach, also called as structural equation modeling, to explain the relationship between variables of interest. For hypothesis testing and extension, this methodology assists the researcher in testing or validating a theoretical model. SEM is nearly 100 years old statistical method that has progressed over 3 generations. The first generation of SEMs developed the logic of causal modeling using the path analysis. SEM is also an earlier name of path analysis and is very powerful in testing and developing the structural hypothesis with both direct and indirect causal effects. It is popular in many fields such as social sciences, business, medical and health science, and natural science. In this video, we are going to quantify relationships among variables by creating a path diagram. The dataset consists of 2 factor variables and 9 response or observed variables, and 1 variable that represents the repetitions of each experimental unit. The first 3 observed variables, ABA, PX, and POD, reflects the activity of phytohormones. The variable pH represents the height of the plants. The third category of variables consists of number of tillers, panicle length, grains per panicle, and 1000 grain weight are considered as the yield contributing variables. To import the dataset, I have placed the Excel data file in the project working directory. Load the library read Excel to access its functions. Create an object data and assign to it a function which I am calling as a read_Excel. In argument path, after the equal sign, within quotations, just press tab button to access the files present in the working directory. Now we need to choose the respective Excel data file. In the next argument, column names, type true to indicate that the first row of the data file contains variable names or headings. In the next line, we can use the head function to print the first 6 rows of the data frame. Here I am converting the first 3 variables as factor variables by using as.factor function. Use attach function for the data object to mask the components of the variables in the data frame. We shall cover up path analysis in 3 steps. These steps include model specification, model estimation and identification, and in the last step we shall plot a path diagram. In the first step, we shall specify a model, and one can do this by using the relevant theoretical and research-based information to decide which variables to include in the model and how these variables are related. Model specification involves determining every relationship and parameter in the model that is of interest to the researcher based on the common knowledge. I have divided variables into 2 categories, one representing the latent variables and the second category includes the observed variables or identifiers. So the main objective of the study is to see how these variables are affecting the kernel yield in rice crop. I am excluding the variable plant height since most studies have shown that it has the least effect on the crop yield. In this example, I am specifying mod ID as model where latent factor, which I am calling as EA, which basically represents the enzyme activity. There is an equal sign followed by tilde, and on the right hand side there are observed variables. So the latent variable EA is indicated by these observed variables in the dataset. Similarly, I have specified another latent variable YC, which basically represents the yield contributing factors. This latent variable is indicated by these observed variables on the right hand side, which are separated by plus signs. The observed variables are the variables that have significant contribution towards crop yield. The next 2 lines are the regression lines. Here the variable GY is the function of enzyme activity and yield contribution. Model identification addresses the question whether or not it is possible to generate unique estimates for a collection of model parameters. So in the next line we have mod EST object, and you can see we are using the SEM function for model estimation. Inside the parentheses, we have model argument where we need to specify the model object which contains the model specifications. Then we have data argument which specify the data object containing the data frame. In the next line, type summary and in parentheses write mod.est to get the model information. We can see that here we have chi-square model fit test and its degrees of freedom. Chi-square tests the hypothesis that there is a mismatch between model implied covariance matrix and the original covariance matrix. Therefore, the non-significance discrepancy is preferred. For optimal fitting of the chosen SAM, the chi-square test would be ideal with probability greater than 0.05. In the next section of latent variables, you can see the first observed variable has loading fixed at 1, so there is no test associated with those, but we have significant tests associated with the remaining variables. In the next section, we have regressions. We can see here the regression coefficients for latent variables and their significance. You can also see that we have a covariance between enzyme activity and yield contribution. The probability value shows a significant directional relationship between the enzyme activity and yield contribution. If you want fit of the Meyers in summary function, then type fit.Meyers equals true. Now in the output, by scrolling up, you can see we have root mean square error of approximation and standardized root mean square residual. RMSE is a badness of fit index where 0 indicates a perfect fit and higher values indicate the lack of fit. It is useful for detecting model misspecification and less sensitive to sample size than the chi-square test. SRMR is similar to RMSE and should be less than 0.09 for a good model fit. Comparative fit index represents the amount of variance that has been accounted for in a covariance matrix, and its value is less affected by sample size than the chi-square test. The value for CFI ranged from 0 to 1. A higher CFI value indicates a better model fit. In practice, the CFI should be close to 0.95 or higher. Our CFI is close to this threshold, which indicates a better fit of the model. Next, we can see there is a Tucker-Lewis index, TLI, which is a non-normed fit index that partly overcomes the disadvantages of NFI and also proposes a fit index independent of sample size. A TLI of more than 0.90 is considered acceptable. Next, we also have the values for AIC and BIC, and these are two relative measures from the perspectives of model selection rather than the null hypothesis test. AIC offers a relative estimation of the information lost when the given model is used to generate data. BIC is an estimation of how parsimonious a model is among several candidate models. Now to look at the path diagram, we have to load the SAMPlot package. Now we can use the SAMPaths function associated with this package. In SAMPaths function, the argument object specifies SAM model. The next argument specifies what should the edges indicate in the path diagram. The value path for this argument will display unweighted gray edges. Next, we need to specify what the edge label should indicate in the path diagram. You can type PAR or EST for this argument to display parameter estimate in edge labels. Running this command will return a path diagram for the model specified. To make this path diagram more appealing, I need to make some tweaks by adding a few additional arguments. These parameters will affect the color and size of the values and text as well as the rotation of the diagram. This is finally how the path diagram will look like. In this path diagram, we can see that observed variables enclosed in squares or rectangles and latent variables are in circles or ellipses. Single-headed arrows or paths, we can say paths, are used to define causal relationships in the model. with the variable at the tail of the arrow causing the variable at the head. The double-headed arrows pointing the two variables shows the covariance between them. The double-headed arrows pointing the same variable represents the variance associated with the variable, but it is often omitted if the variable is standardized to unit variance. I have received some suggestions where the followers asked me to make some videos on most commonly used packages in R. So in the next videos, I'm going to explain the functions used in the commonly used packages. Most probably I shall start with the dplyr package first. Hope to see you in the next video.